Okay, so we have an idea of what vectors are, and we can draw those vectors, and we can even do some operations with those vectors in that form where we see in that visual graphical form of the vectors. But of course, we can't spend all our time just drawing out vectors, so we need a better, simpler way to deal with vectors, and that's going to be what we call this component form of a vector. And here's how this is going to work. Let's take a look at the point. Uh, let's just consider. How about we consider 2 points? The point A, which will have the coordinates of 2, -1. So back in the world of R2 here, 2 dimensions. Just about drew an R. And B at, let's say, 3, 2. So we know exactly what we're talking about here. Here's X, Y. And A is this point 2, -1 right here. And B is a point 3, 2 right here. Okay, I want to define this vector. Here's my notation, AB, with an arrow going across that way, as the vector from point A to point B. So it's going to be this vector right here. Now, how are we going to say what the direction of magnitude is? Well, it's very simple. We just say how far to the right we go or left, and then how far up or down we go. And so that vector AB we will find by taking the components, the x component of B minus the x component of A. So where we end minus where we started, that's always the order. And then same thing for the y components. Where we ended minus where we started, 2 minus a minus 1. Now the notation we use for vectors in component form is this sort of pointy brackets here. So we end up with AB, the vector from A to B, being the vector 3 minus 2, which is 1. 2 plus 1 is 3. And you can see that's how I get from point A to point B. I go to the right 1 and up 3, to the right 1 and up 3. And that gives me my vector from A to B, the vector AB. Now, if I want to write this as a position vector, let's go ahead and define what that is right now. A position vector is just a vector which starts at the origin. So I can make a copy of this vector AB and make it a position vector by just going to the right 1 and up 3 starting from the origin, and there it is. But again, remember that we can put those vectors anywhere we want as long as their direction and magnitude are the same. So it gets harder to draw vectors when you get to R3, but let's just take a look at an example. Let's let P be the point 3, -2, 1. And Q be the ordered triple 4, 5, -6. Again, a little bit messy to draw, but I can find the vector PQ. So that's the vector that starts at point P, ends at point Q. And again, we're going to take the corresponding the components of Q and subtract the corresponding components of P. So we'll have 4 minus 3, 5 minus a minus 2, and -6 minus 1. And so that gives me the vector PQ to be 4 minus 3 or 1, 5 plus 2 or 7, -6 minus 1 is -7. Now you can check that if I ask you to find QP, that's a different vector because it's going in the opposite direction. It will just be the negative of PQ. So if we turn the vector around, the components just become the opposite of what they were. And so this makes it much easier then to combine vectors as we were doing before, pushing those arrows around. If we want to combine vectors in this component form, I think you will find it is quite simple. Let's let A be the three-dimensional vector 3, -2, 4, and B be the three-dimensional vector 5, -1, and 7. All right, let's suppose I want to find, how about first of all, we'll find A plus B. Well, we just add the corresponding components. So it's going to be 3 plus 5, -2 plus -1, and 4 plus 7. So the new vector that we get is, let's see, 8, -3, and 11. That ain't so bad, is it? And of course we can bring some scalar multiplication into play. 2a minus 3b, say. So that's 2 times the vector 3, negative 2, 4, minus 3 times the vector 5, negative 1, 7. And of course, scalar multiplication in component form is just what you'd think. You multiply it through all the components. So we're going to have 6, negative 4, 8, minus, you can take the negative and distribute it too. I'll leave the negative out front. Just bring the 3 through. So 15, negative 3 times 7 is 21. So now I'm going to subtract. 6 minus 15 is a negative 9. Negative 4 minus a minus 3, it's negative 4 plus 3 is negative 1. And 8 minus 21, oh boy, I guess negative 13. Alright, so ain't so bad, huh? Now, I've talked about this idea of distance. Another way to say that is magnitude. So let's talk about finding the distance or magnitude of vectors. And of course, I shouldn't say distance. I want to say length. I mean, you can think about it as a distance from the starting point to the ending point. Let's suppose I wanted to find the magnitude of this vector. Let's call it vector A, and let's say it has components 2, negative. Actually, let's make it 2, positive 3, 5, so we can see a little bit better. We're going to put it as a position vector, and so we're going to go out 2 over 3 and up 5. This seems to be always the way I illustrate things graphically with this point. I don't know why that is. So if we draw it as a position vector, in other words, starting at the origin, we're starting here at the origin, ending at the point 2, 3, 5. And so, well, it's just the distance formula from the origin to 2, 3, 5. And so the magnitude of A, the notation we use is the absolute value symbol, is equal to the square root of the first component squared plus the second component squared plus the third component squared. So that is the square root of 4 plus 9 plus 25, which I believe is the square root of 38. And so if we're given any vector, call it u, u1, u2, u3, the magnitude of that vector is going to be the square root of the components added together. And that, of course, is not just for three-dimensional vectors, that's for, so here's a little mistake. I don't need vector signs. These are real numbers in the components. Don't need vector symbols here either. Take the components, square them, add them together. Take the square roots. That is the magnitude of a vector. Now I want to take a quick look at the properties of the vectors just to highlight a couple of those. Main ones here that we're looking at. A plus B is equal to B plus A. That, of course, is the commutative, well, you know how to spell it, commutative property. We also have this associative property that we have not mentioned yet, associative property right there. We have our additive identity that we've talked about, the zero vector. We have an additive inverse. Scalars distribute across the sums of vectors, and vectors distribute across the sums of scalars. We have associativity of scalar multiplication, and we have our multiplicative identity, multiplicative scalar identity. 1 times the vector is equal to the vector itself. Okay, and a couple other standard things here. We can get them on this page, I think. If we talk about V sub 2, we're talking about the set of all two-dimensional vectors. So vectors that we could draw on the R2 plane. If we talk about V3, we're talking about the set of all three-dimensional vectors. So the ones we've been looking at mainly for our examples, but this can expand. If we have component-wise vectors, of course, it's very difficult to draw once we get past 2 or 3, but we can certainly talk about V sub n. We can talk about any dimension. The set of all n-dimensional vectors, we will call that V sub n. Now, we also have what is referred to as, well, let's just go to the next page here, our standard basis for, we'll go ahead and do it for V3, but I think you'll be able to see what it is for other dimensional vector spaces as well. I is going to be the vector 1, 0, 0. The vector j is the vector 0, 1, 0, and k is the vector 0, 0, 1. So we can see where those lie in R3. The reason we call these bases is that we can form any vector in V3, in our three-dimensional vector space, out of those three vectors. So here is the vector I, here is the vector j, and here is the vector k. Now, what's nice about this is that, again, we can represent any vector as a linear combination of these three things. So if I were to take, say, 5 times I minus 2 times j plus 3 times k, what's that equal to? Well, 5 times 1, 0, 0, minus 2 times 0, 1, 0, plus 3 times 0, 0, 1. So that's just a vector, well, 5, negative 2, and 3. So oftentimes we will represent our vectors using I, j, and k. You'll see them that way in some of your homework and in the book as well. So we may write 7, 5, negative 3 as 7i plus 5j minus 3k. You may see the vectors represented. You need to be able to go back and forth to go either way. And of course, for V2, as I said, we just have these two, 1, 0 for I, and j is 0, 1. And of course, graphically, those look like this. There's I, and there's j. And you can do the same thing. You can represent any vector in V2, any two-dimensional vector, as a linear combination of I and j. Now, what do we notice about these vectors, I, j, and k in V3, and I and j in V2? Well, they all have length 1. In other words, we see that the magnitude of I is the magnitude of j, is the magnitude of k, which is equal to 1. Since they have length 1, we refer to these as unit vectors. Alright, so any vector of length 1 or magnitude 1 is what's called a unit vector. Not just those standard basis vectors. Any vector of magnitude 1 is what we refer to as a unit vector. And so we can do what's called unitizing a vector. Let's suppose we have the vector u, and it's given by these components, 3, negative 2, 1. What I want to do is find, let's suppose, a unit vector in the direction of u. So what we're going to do then is find the length of that vector, and then we're just going to scale that vector down to length 1. So what's the length of the vector u? Well, remember what we do. We square the components, add them together, and take the square root. So it's the square root of 9 plus 4 plus 1. That's the square root of 14. Well, think about it. If the length was 2, what would I do? I'd cut it in half. I'd multiply the vector by 1/2. So what I'm going to do then is I'm going to, instead of cutting it in half, we're going to take the length times, the length times the vector itself. So here's how it's going to look. 1 over the square root of 14 times 3, negative 2, 1. Or if you like, 3 over the square root of 14 in the first component, negative 2 over the square root of 14 in the second component, 1 over the square root of 14 in the third component. Okay? But in general, to unitize, you just take the vector, divide it by its length. That's how you can find a unit vector for any direction. And so then you can do some other things with that as well. Let's suppose I want to find a vector in the opposite direction of v of length 6. And let's suppose v in this case is 2, negative 5, negative 3. Well, the first thing I'll do is I'll find the length of that vector. So it's going to be the square root of 2 squared plus negative 5 squared plus negative 3 squared. Oh, that's 425 and 9. So, square root of 38 again. What do you know? I must like those numbers. Okay, so a unit vector in the direction of v is going to be v divided by its length. It's going to be this vector 2 over the square root of 38, negative 5 over the square root of 38, negative 3 over the square root of 38. So same direction as v, length 1. We want opposite direction, length 6. So let's turn it around. Now it's opposite direction, length 1. And then finally, let's multiply it by 6. So negative 6 times v over the magnitude of v. And so we've got a positive 12 over the square root of 38. Positive 30. Let's see, make that negative 30, right? Oh, let's see, I've just taken 6 times this last one, so that's negative. Yeah, that's positive there. And this is going to be negative 6, yeah, so 18 times that. Just taking that last one times 6, so the signs stay the same. And if you like, a lot of times what we'll do is leave the length out front. Negative 12, 30, 18. You can also factor things out. I mean, 6 is a common factor here, so you could say, well, you could say 6 over the square root of 38 times negative 2, 5, and 3. That's another way to represent it. Okay. So we're going to conclude then with one application problem here. I think you'll have a couple that you can look at using vectors. Let's suppose that a plane has a heading of south 30 degrees east with a speed of 300 miles per hour. Let's also suppose that a wind of 40 miles per hour is blowing from, that's from the direction of north 45 degrees east. That, of course, is going to affect the course of the plane. That's what we want to find. We want to find the true course of the plane. So what we're going to do is we're going to represent the heading of the plane and the direction of the wind with vectors. So let's go ahead and let P be the heading of the plane, the way it's flying, and W be the vector representing the wind. Okay, so we want to be able to write these in component form. We can see visually basically what's going on here. So we've got north is straight up, west, east, and south. Now the plane, if we write it as a position vector, south 30 degrees east, so we go due south, rotate 30 degrees to the east. So our plane, let's make it here, is going to be this vector, and the length is going to be 300. The wind is blowing from north 45 degrees east, so I face north, 45 degrees to the east. That's the direction it's coming from, so as a position vector, let's go this way. It has length of 40, so much shorter than that other vector. We can put it like that. And so if I'm going to tack this wind on here, my true vector, my resultant vector, is going to be something like this. It should be something to the south, rotate a little bit towards the east, and a little bit longer than 300, a magnitude of a little bit longer than 300. I hope you can see how we got that. So here is P, the heading of the plane originally. Here's the wind vector. If we add those together, we get this P plus W vector right here. Okay, so let's see how we can do this then. Let's let P, let's let P be something times I, that's not an I, is it? Plus something times J. Two-dimensional vectors, we can represent it with those I and J's. Now, if we think about it, this angle off here is 30, so this angle is 60 degrees off of the horizontal. So if I think about trying to get the components here, I'm going to go this far in the east direction, the positive x direction, and this far in the positive y direction. There's A, make sure we can see this, A here and B here. Okay, well, I'll use a little trig here. Yeah, so the cosine of 60 degrees is A over 300, right? So the cosine of 60 degrees is A over 300. So A is equal to 300 cosine 60. The cosine, well, let's just leave it like that for now. Opposite over hypotenuse is sine. So the sine of 60 degrees is B over 300, which tells me that B is equal to 300 sine of 60 degrees. let's see, the cosine I think is 1/2. The sine is square root of 3 over 2. And so I can represent my vector P here as, well, let's see, 300 cosine of 60 degrees I. But now notice that B is going in the negative direction. So I'm going to write this as minus 300 sine 60 degrees J. Or if you like, in this component form, 300 cosine 60 negative 300 sine 60. Okay, we can do something similar for W. If I say W can be represented by Ci plus dj, so here we're going to go C and D. Both of those are negative, but the reference angle here is 45 degrees, recall. So, well, let's see here. C is going to be given by the cosine of 45. Cosine of 45 degrees is C over the length of the wind vector was 40, remember. So there's our hypotenuse. Okay, so C is 40 cosine 45 degrees, and of course the sine of 45 degrees is going to be D over 40. It tells me D is 40 sine 45 degrees. Both are negative, so W can be represented as a negative 40 cosine 45 degrees in the I direction minus 40 sine 45 degrees in the J direction. And so P plus W, then we're just going to add these two components, and it's going to look a little ugly here, but it is what it is. P is going to be 300, or P plus W rather, is 300 cosine 60 degrees minus 40 cosine 45 degrees, and the second component is combining the two second components of our plane vector and wind vector, so that'll be a negative 300 sine 60 degrees minus 40 sine 45 degrees, and there you have it. Of course, you could run that through your calculator and get some decimal approximations. You can, cosine of 60, of course, is 1/2. Cosine of 45 square root of 2 over 2. Sine of 60 square root of 3 over 2. Sine of 45 square root of 2 over 2. So you should know those at this point in your mathematical careers. But that tells you what it is. So you can find the length of this vector then. You should get something bigger than 300. And of course you should get a little bit of a positive in the first component because you are going a little bit to the right here. We're going a little bit to the right and then down. Big negative, a little bit of a positive. So take this minus this, it should still be positive, and of course these two are going to give you a pretty large negative. Okay, you're in good shape now for 9-2. Just need the password for the homework, and here it is. Foppery, F-O-P-P-E-R-Y, and that is just a foolish character or action, sometimes associated with vain people. Engage in foppery, foolish character or action. Good luck on 9.2. If you get stuck, if you have any questions at all, please let me know.